Hi, this is Jack Jackson. We're going to look at the triangle angle sum theorem. Okay, so let's take a look and see if we can make a discovery here. So let's look at uh, this sketch here, GeoGebra activity. Oh, that link was not working. Let's get to it this way. Geometry collected resources. Let's look under triangles in Euclidean geometry. And then let's see here. Sum of the interior angles of a triangle. Okay. Let's just start with this one. Okay, and let's open this in the app. So here's a triangle in Euclidean geometry, and we have everything measured. We should be able to, okay, so we can see A, B, and C now, and they're free points that can be moved anywhere. Of course, if they're collinear, we don't get a triangle, but otherwise we get a triangle there. I've got the sides measured using the standard Euclidean metric there. And then we can see the interior angles are actually uh, raised there. And then I can mark them, let's see, this way with their measures. And here we have their measures. I've got the measures of these angles right here. And they're actually measured in uh, radians and degrees. Point, see, this is this one up here. This one is the red one, it's here, and this one is the blue one here. Okay, so it's 0.23344 approximately radians. That's approximately 0.07 pi radians or 13.38 degrees. Okay, and here we have this one measured in degrees and radians. Here it is measured in degrees and radians. Of course, this is dynamic as we move this around. These links and things change. But if we add these up, which is what this is doing, it's just actually adding the measure of those angles, see? And notice that it always turns out to be pi radians. Isn't that crazy? About, okay. So it's always pi, or sometimes it's approximating it there. But it's always pi radians. Or if we did it in degrees, what would we get? 180 degrees. So that's an interesting thing here. Okay, so that the angles always sum up, the measures of the interior angles always sum up to 180 degrees or pi radians. Now let's quickly look at some other geometries and see what happens there. Um, if we go to hyperbolic geometry and do the same thing, I'll just do it right here. Let's go ahead and open the app, it works better. So here we have our triangle in hyperbolic geometry, and we have our sides measured and our angles measured as we do in hyperbolic geometry. And if we add those up, notice that it's not 3.14, it's less. It's less than pi. So if you take pi minus this number, we're under by a certain amount. That's called the defect in that triangle. And so there's always some defect where no matter what we can get, we're always less than pi here. Okay? And we can get it, we can get it closer to pi, but we can't actually get it to be pi. Okay? So the angle measure is always less than pi in hyperbolic geometry. Okay, what about spherical geometry? Here's one, a general triangle in spherical geometry. Okay, and so here we have the angles. I've got their measures actually over here. Okay, and so they're also here too. So this one's about 0.94, 1.6 something, 0.9 something. Well, if you add those up, this is about 3.59 radians. That's bigger than pi. So it's about 1.14 times pi, or it's about 205, almost 206 degrees, more than 180 degrees. So you have an excess here. You've got an amount over 180 degrees, amount over pi. And so that's called the excess, which is pi minus, actually that's incorrect. It's the sum minus pi is the excess. So the sum of the angle measures is bigger than pi. Subtract pi from that and you get the amount that it's over, in this case about 0.45 or about 25.8 degrees. It's more than 180 degrees by that amount. You can get it to be quite a bit. You can get the measures, the angles to be really big, get a big excess. Or we make the triangle kind of small. We can get that excess small, less than a degree, but it will never be zero in the excess. The angles will never sum up to pi radians or 180 degrees. They'll always add up to something more than that. Okay? Now, so it turns out that the angle sum thing depends on which geometry you're in. Of course, taxicab geometry is the same as Euclidean geometry when it comes to angles. So let's look a little bit more and look at this here and see if we can come up with something interesting. Let's see what I might want to look at. I think I want to look at this one. Okay. So let's see what this does. Okay. So look what they've done here. They've said, okay, if you take this angle basically and slide it over and rotate this one around, what do you see? You see that they all add up. That might help you with a proof to see that those three angles add up to the same as a straight angle, pi radians or 180 degrees. Okay, that's the GeoGebra team's way of looking at it there. Let's see if there's another way to look at it here. Yeah, this one's an interesting one. I like this one. So there's the interior angles. Look at what he's doing here. He's rotating those angles up. Pop. They make a straight line there, so in fact they add up to 180 degrees. Oh, how about the exterior angles? This is interesting too. Look what happens here. They sum up to 2 pi. They sum up to 360 degrees. That's pretty interesting. Okay, so we can see some interesting things there about the angles. Okay, how can we go about proving this thing about the sum of the angles being measured, some of the angle measures being pi radians or 180 degrees? Well, a hint is that it has something to do with the parallel postulate. Okay, so what does the parallel postulate say? It says, let's say you take this side BC, there's exactly one line that's parallel to this line through this given point. There's only one. Now, what did we just prove in our most recent videos? We proved something about the Z property, right? That if we're going to take this, let's just do this so I can make some angle measures here. And if I measure this angle here, we can see that that angle there, I'll get it color coded with this one. Whoops, didn't mean to do that. I want to select this angle measure marker. And notice that red angle there is the same measure as that. Why? What property is that? Well, those are actually, I'm sorry, that's not right. It's the same as this one down here. Okay, should be colored whatever this one is, blue. Because there's your Z property. See the Z right here? They're alternate interior angles when you have a transversal. Line AC is the transversal. This is line segment AC is part of that transversal. And you got line up here, the parallel line to the line containing the base here. We got our interior angles there. They have to be, alternate interior angles must be congruent. Well, similarly, you've got a Z on this side. So this angle here, okay, we want to make sure that that angle is what, it's between 0 and 180 degrees. And we also want it to be the same color as this one. This is the one that should be red. Because notice that that measure and that measure are the same. And so those are congruent. And again, it's by the Z property that we get that to happen. These two angles are congruent. And by the Z property, these two angles, the one down here and the one up here, are congruent. So in fact, what do we have? We have this. But what do you notice? Wait a minute. What do we notice about this? This is a straight line after all. And so the angle measure theorem, or angle measure postulate, says that these three measures must add up to the measure of the straight angle, which is pi radians, or 180 degrees. So there's your proof that the angle sum works. So we have proved, using the Z property, we have proved that the sum of the measures of the interior angles of a triangle in Euclidean geometry is, in fact, 180 degrees, or pi radians. But notice we use the direction of the Z property that only works in Euclidean geometry, not it doesn't work in hyperbolic geometry and spherical geometry. So we get a different result in those geometries. So once again, in Euclidean geometry, the angle measures sum up to pi. In taxicab, you get the same result, different length measurements on the triangle, but the angle measures are the same. In hyperbolic geometry, the sum of the angle measures is always less than pi radians, so there's always a defect, amount that you're underneath that. And in spherical geometry, the angle measures always add up to something between pi and 3 pi, non-inclusive. And there's always an excess, an amount above pi radians. Okay? And so, again, now we have the Euclidean triangle angle sum theorem. So once we prove the Euclidean triangle angle sum theorem, what should be the next question? Well, we could ask, does it generalize in any way? Does it work in other geometries? We see that it does not. It's a similar but a different kind of result there in the other geometries. Well, one thing we might ask is, what about a n-gon? If we take an n-gon and look at that, can we say something about the sum there, say for a quadrilateral or a pentagon or hexagon and so forth? Now, we are going to run into something, well, let's actually just investigate very quickly in GeoGebra. Let's go back here. So let's just go to GeoGebra's regular site, go to Classic, and we're going to, on the fly, create something here. So we're going to create a quadrilateral real fast. Just a general quadrilateral. And let's go ahead and do the angles. Okay, before I do this, can you tell me what the angle measures are going to add up to? Okay. So there are all the angles, but they're not measured like we measure angles. Let's measure them around this way. So we want all of those to be between 0 and 180 degrees. We're measuring in, looks like we're measuring in radians. That's my default. Yours might be degrees. That's okay. All right. I'll tell you what, for this one, well, let's leave it like that. Okay. So we have that. Now let's actually measure, add them up. Let's actually just do it in degrees for this one. So let's go over here, do our angle in degrees. So there's the angles measured in degrees, not necessarily the same as each other. Okay. What about adding them up? Okay, so let's actually compute that. Here's a way we could do that. Let's just go ahead and do a text here, and let's just say we've got angle alpha plus angle beta plus angle gamma plus angle delta, and it equals, and alpha, but let's say I want to go here, plus beta, oops, well, let me do that. Let's see. Let's see if I can get it down here. Beta. Can not do it inside here? No, it's not letting me. Okay. So let me do a workaround here. Okay, so doing a workaround, we're going to rename these angles. Okay, I'm going to click on this and just rename it little a instead of alpha. And I'm going to rename this one. It's at B, so we'll name it B, little b. We'll rename this one little c, and we'll rename this guy D. Okay, so let's go ahead and find the sum. So let's go here again. We'll just do it in a text box. So I want to say we want to give it the value of A plus the value of B plus the value of C. Now this will just going to display these things on these specific values on there, and then equal. And then we want a box that says A. Whoops. Push down arrow to get on the other side, and then A. And I want to modify this box to be plus B plus C plus D. I believe that will do it. Yeah, there it is. It added them up. It's 360 degrees. Did you think that was going to happen? Well, look at it. As we move around, sure enough, it's still 360 degrees, right? Well, how can we see that? Well, one thing we could do is just draw a line segment, one of the diagonals like this. Well, if you see, these three angles inside here add up to 180 degrees. These three add up to 180 degrees. And if you add them all together, you'll get these two. And then, of course, adding these two is the same. Two smaller angles here at A adds up to the same thing as the bigger angle at A, the interior angle. Same thing at this end. I think you can see you get a proof. There's only one problem with that, and that's as if you have this situation here. Now it's not adding up because the interior angle B actually measures as this angle, and this no longer works. In that case, it's useful if you can measure this angle a different way. Okay. So this time, let me change the color on it. And versus this one here. So if you think of this as 139 degrees here, this angle here to finish out the full circle is 220. Well, if you look, if you'll add this angle, and look at this diagonal here, now you can see your two triangles here. And if you add this angle, the original angle at A, C, and D, and then look at this angle here, it can be found by adding these two interior angles and the one at D of adding these two angles together. So these angles add up to 180 degrees. These add up to 180 degrees, or pi radians. And we see that it does add up, but only if you use this red measurement of the angle here instead of this one. So in the case when you have a convex quadrilateral, okay, or in general a polygon that's convex, has a convex interior, concave, not a, if it's convex, everything's golden, right? It adds up to 360 degrees. But when it's caved in here and it's concave, then we have what we call a reflex angle here, where the interior of this angle, which is technically this part in here, does not intersect the interior of the triangle. That's where it's caved in, and we have a reflex angle. In that case, measure the reflex angle as 360 degrees minus the measure of that angle. So 360 degrees minus this 93.25 is the measure of that red rotation, 266.75. In the case where it's caved in there, there's a reflex angle at that point. Use the measure of the reflex angle as a reflex angle. In other words, use this red measurement. Then, in fact, they do add up to 360 degrees again. Okay? So that was a situation didn't really show up with Euclidean angles, but this talks about how we can do that. Reflex angles will be in the interval from pi to 2 pi, or 180 degrees to 360 degrees. Okay, and so here's an interesting task for you. If the number of diagonals of an n-gon, what is it? Let's just look at it from a table here. So in a triangle has 3 sides and vertices, no diagonals at all. Sum of the interior angles is 180 degrees. If it's an equiangular triangle, it will have 60 degrees, or pi over 3 for each one. What about a quadrilateral? Well, from each vertex, there's one diagonal. There are 4 vertices. That would give you 4 diagonals, except you're counting each one twice. So divide by 2, and you get 2 diagonals. The sum of the measures of the interior angles was 360 degrees, because you're forming, take the number of diagonals at one vertex will always give you one more than the number of diagonals at each vertex will be how many triangles you have. And so we have that. So this pattern keeps going. For a pentagon, you get 2 diagonals at each vertex for a total of 2 at each vertex, right? So that's 2 times 5 is 10, divided by 2 is 5 total diagonals. And if you take the diagonals at one vertex, you're going to end up with 3 triangles there. So 3 pi, or 540 degrees, is what you get. Divide that by 5, and you get the angle of a regular, or just an equiangular pentagon. Okay? And this pattern keeps going here. So the number of sides and the number of diagonals from each side goes up by 1. So the number of sides and the number of vertices is n for an n-gon. The number of diagonals is n minus 3. The total number of diagonals is then n times n minus 3, but then you have to divide by 2 so that you don't count them twice. And if you have n minus 3 diagonals, you actually have n minus 2 triangles formed from the diagonals at one vertex. So each one of those adds up to pi, so the total angles add up to n minus 2 times pi radians, or n minus 2 times 180 degrees. Take that value and divide by n will be the size of the angle in a equiangular n-gon. Now, given what we know about the measures of interior angles of other triangles, we can get this. In a triangle, taxicab, and Euclidean geometry, they add up to pi. They're between 0 and pi, and hyperbolic, between pi over 3, and spherical. In a quadrilateral, what's that going to do? That's where we're really studying this unit. We have the sum of the measures is 2 pi in taxicab and Euclidean for the measure of the interior angles. It'll be less than that between 0 and 2 pi for hyperbolic, and more than that between 2 pi and 6 pi for spherical. Okay. Pentagons, we just saw it's 3 pi here for taxicab and Euclidean, less than that for hyperbolic, more than that for spherical, and so forth. Or in general, n minus 2 times pi for taxicab and Euclidean geometries, between 0 and n minus 2 pi exclusively for hyperbolic, bigger than n minus 2 times pi and up to 3 times that for spherical geometry. And here's another curious result. It turns out if the sum of the measures of the interior angles of a triangle is a constant, then that constant must be pi radians, or 180 degrees. And I'll leave that as a homework task for you to prove. Okay, so now we know a lot about the sum of the interior angles of some of the measures of the interior angles of triangles in various geometries. And we know from that we can get the sum of the various measures of the interior angles of any triangle or any pentagon. We are measuring angles as reflex angles. We are measuring as reflex angles where appropriate.